So let's go over quiz number 4. Number 1 says NaOCl is the chemical formula of common household bleach. What is the chemical name of this molecule? So over here, Na we know represents sodium, and the question is, what is this polyatomic ion? That would just be something that you'd look up on a table and remember. And so the name of OCl minus the polyatomic anion is hypochlorite. Hypochlorite. So NaOCl would be called sodium hypochlorite. The correct answer for number 1 is C. Number 2 says, what is the charge on iron in FeNO2 3? So this question looks a lot like one of the questions we had on the worksheet, and that question was where we were looking at CuNO3 2. And if you remember, we established that NO3 carries a -1 charge. So if you have two -1 charges, in order to balance that out and make a neutral molecule, this copper had to have a +2 charge. So we can relate what we learned here to figuring out what the charge on the iron is in this molecule. So we would have to know that NO2 happens to also have a -1 charge. So if we have 3 -1 charges, how many positive charges do we need to have in order to balance that out? We would need to have 3. So therefore the charge on the iron would have to be a 3+ in order to balance out the 3 negative charges from the 3 NO2s. So just like that, the iron over here has a 3+ charge. So the correct answer for number 2 is C. Moving on to number 3. Number 3 says, which of the following describes the trend of electronegativity across the periodic table? So in order to answer this, let's make a model periodic table so we have something to reference as we're discussing it. There we go. That's kind of what it looks like. A says electronegativity increases from top to bottom and right to left. So let's look at one at a time. So it says here that electronegativity increases from top to bottom. So from top to bottom. This is saying that the electronegativity goes up from the top of the periodic table to the bottom. Well, I don't know about that because of electron shielding. We know in fact that electronegativity goes up as we go up a group, and it goes down when we go down the group. This is because the nuclei in the atoms farther down in the table become more shielded, so their electronegativities actually go down. So A is clearly incorrect because it suggests the opposite of what is true, so we can go ahead and cross that off. Electronegativity increases from bottom to top. Okay, that's agreeable. So we go from bottom to top, our electronegativity goes up because our atomic radius now becomes smaller and we do less shielding. So that's good. And then it says an electronegativity increases from right to left. That doesn't sound right, because we know from our periodic trends that if we go this way along a period, our electronegativity goes up. So we're going actually from left to right. This is because as we move from left to right along a period, we have an increasing number of protons in the atom. So with more protons, we have more attraction for those electrons, and therefore the electronegativity of the atoms goes up. So electronegativity increases from left to right, not from right to left. So B would also be incorrect. We can cross that one off. C says electronegativity increases from top to bottom. Well, that sounds a little bit like A, so I think we can probably get rid of C as well. And with that, we're left with D, which says that electronegativity increases from bottom to top. Yep, we agree with that. And from left to right. Sounds good to me. So the correct answer for 3 is D. Number 4 says, order the following substances, or elements, they're elements, according to increasing electronegativity. So here we've got lithium, bromine, lead, potassium, magnesium, and carbon. So lithium's going to live somewhere over here, and bromine is going to live somewhere over here. Lead is going to be somewhere in the transition metals. We've got potassium here, we've got magnesium over here somewhere, and we've got carbon that lives right about there. What you can do is, on the quiz you were given the periodic table, an actual table. What you can do is you can use your knowledge of how the electronegativity trends across the periods and up the groups to see which of these elements is going to have, first of all, the least electronegativity. That's going to be the one that's farthest down in this corner, and order them in increasing order as you move up this way in the periodic table. So the correct answer, if you do that, for number 4, turns out to be B. Then number 5 says, which of the following would you expect to have non-polar covalent bonds? So first of all, let's remember how we can use electronegativities along a scale to tell us about whether the bond is polar or nonpolar. So if you remember this, if we see here that the electronegativity difference, which we calculate from tabular values, then we see here that the electronegativity difference being between 0 and 0.5 indicates that we have a nonpolar bond. And then between 0 and 2 means that the bond is polar. And then anything beyond 2 would give us an ionic bond. Okay, this will come in handy. So let's look at A. We've got calcium and we got chloride. Does that sound to you like something we've heard before? I wonder if it sounds like a metal and a non-metal bonding. Yeah, because calcium's a metal and chloride is not. It's a halogen. So A, we can cross off because that's going to be an ionic bond, absolutely, because we have a metal and a non-metal. B is titanium-3 chloride. Well, titanium lives in the transition metals, and chloride is a halogen, so again we have a metal and a non-metal, and we can cross that off because we know that's going to be ionic for a fact. C, we've got lithium, lithium and fluoride, so fluoride's going to be somewhere right up here. Lithium's a metal and fluoride's a halogen, which is a non-metal. So we've got a metal and a non-metal bonding. We can nuke C. So C is not correct because that's going to be ionic. And just by the process of elimination, that leaves us with D. So in fact, D is the correct answer. So anytime you have two atoms that are the same, so you got oxygen and oxygen, right? So two atoms that are the same will always have a perfectly non-polar bond. So the electronegativity difference is going to be 0. So if you could imagine, if you wanted to calculate this, it would be like saying, okay, I'm going to find the electronegativity of oxygen and subtract from it the electronegativity of oxygen. Well, you get 0. So anytime you have a bond that's between two identical atoms, like oxygen and oxygen, or carbon and carbon, or fluorine and fluorine, or phosphorus and phosphorus, then that is always going to be a non-polar bond. Its electronegativity difference will be 0. So now, with number 6, we're asking a slightly different question. Which of the following would you expect to have polar covalent bonds? So, first of all, let's start out with A. Here we have cadmium and we have bromide. So let's take a look at the cadmium and bromine bond and find the electronegativity difference for that bond. So it's going to look like this. It's going to be the electronegativity of bromine minus the electronegativity of cadmium. And again, you can do these in either order. It doesn't matter. What you're looking for is the magnitude of that number. You're not worried about the sign, whether it's positive or negative. You're just looking at how big that difference is. then when you compare it to this scale, and that is what will tell you about the polarity. So if you happen to reverse the order of which way you subtract these, don't worry about it. The sign is not what's important here. It's the magnitude of this difference. So I've got the Pauling scale electronegativity table up in front of me here, and I'm just going to go ahead and look up these numbers. So I've got 2.96 for the bromine, and for the cadmium I've got 1.69. So I'm really bad at mental math here. I'm going to go ahead and take these numbers and plug them into my calculator. Okay, and I get 1.27. So where does 1.27 lie on this scale? Well, it's going to put us somewhere right about here. That is clearly a polar bond. So therefore, A will be a correct answer. C is calcium chloride. So let's go ahead and actually examine the polarity of this bond. Let's go ahead and do that. So the electronegativity difference between calcium and chlorine is just going to be the electronegativity of the chlorine minus the electronegativity of the calcium. There we go. So this is 3.16 minus 1.00. Okay, I don't need a calculator for this. I can do this. This is easy. This is my kind of mental math. We go 2.16. Alright, so this is the electronegativity difference of a calcium chloride bond. Well, that lands us somewhere right in here. And our intuition here from number 5 saying that the calcium chloride was an ionic bond was correct. But when we actually went in and calculated the electronegativity difference, it turned out to be more than 2. So therefore B, calcium chloride, would have ionic bonds, and therefore they're not polar covalent, so we can cross B off. So B would not be a correct answer. C, well, we just talked about what happens when we have two of the same atoms bonded together. So here we've got phosphorus, literally phosphorus bonding to phosphorus. We got 4 of them. So just like with the oxygen, oxygen like that. Anytime you got the same atom, same 2 atoms bonded together with the bond, the electronegativity difference is always going to be 0. So that's characteristically a nonpolar bond, and since we're asking for polar bonds, that is an incorrect answer. I have no idea why that C is so small. Anyway, so the last one we have to evaluate is D. So let's go ahead and do that. And I'm going to do this a little bit more quickly, as to not bore you, but I'm still going to show every step, so that it's no mystery as to how I arrived at this answer. So again, I'm just looking these values up on the table, and for nitrogen I have 3.04, okay, and I'm going to be really bad at mental math, and I'm going to plug this into my calculator. That's totally okay, and the number I get is 0.94. So this is the electronegativity value, a difference value for the nitrogen-fluorine bond. Now, is that a nonpolar bond, a polar bond, or an ionic bond? How do we know? We go to the scale, and we see, where does this lie on the scale? Well, it's above 0.5, so it's somewhere in here that's definitely a polar bond. So D would also be the correct answer. So for number 6, if you chose either A or D, I gave you full points. But if you happen to identify that both of them were correct, then thumbs up for you. Good job. So number 7 says, how many electrons are in the molecule ammonia? So the first thing to keep in mind here is that nitrogen has 5 valence electrons. And the other thing to keep in mind is that each hydrogen will contribute 1 electron. So if we have 3 hydrogens, that means that we'll have a total of 3 electrons from the hydrogens, and 5 valence electrons from the nitrogen, which means that the total number of electrons we have is going to be 8. So the correct answer for number 7 is D. Now we can draw the Lewis dot structure to validate our initial assessment. So nitrogen is going to be our central atom, and let's go ahead and draw the valence electrons. So we know there's 5 of them, so here we go. Here's our 5 valence electrons. 1, 2, 3, 4, 5. Then hydrogen's going to come in here, and I'm going to draw the hydrogens now in a different color so that we can see where all the electrons are coming from. So the hydrogens here are going to come in like this and contribute an electron, like this, contribute an electron to that valence electron on the nitrogen. And together, the nitrogen electron and the hydrogen electron are going to be a pair of electrons that covalently, meaning that they are both in the valence shells of each of the atoms, that covalently are going to bond the hydrogen together with the nitrogen. So that's what's happening here when we draw the 2 electrons. One of them is coming from the nitrogen, and the other is coming from the hydrogen. And together, the electron pair is what constitutes the bond between the nitrogen and the hydrogen, the covalent bond. So we can show that here for this hydrogen and this hydrogen, just like that. So this is the Lewis dot structure of ammonia. And we don't have to, but we can draw that, and just to indicate that that's the lone pair. If you drew something like this, where this dash here represents the 2 electrons here participating in the covalent bond, that's totally okay. I gave you credit for that. But what you had to do was you had to clearly denote the lone pair on that nitrogen, because that's really important. That makes the nitrogen neutrally charged, and it also says that the 5 valence electrons, that out of the 5 valence electrons, 3 of them were occupied in a bond, and the remaining 2 formed a lone pair. The third reason that that's important is because that determines the geometry of this molecule, and we'll see that in number 10. So you had to just include the nitrogen is your central atom, 3 hydrogens around it, somehow indicating that they're bonded to the nitrogen, and you had to include a lone pair. So that's what I was looking for in the Lewis dot structure of ammonia. Number 9 asks, how many electrons are in the ammonium ion? So let's go ahead and draw the structure of ammonium. We got N, H, 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 and H. And we got to remember that it's positively charged. So what I like about drawing the structure first is that I can now recognize where my electrons are, and I know what to count. So let's go ahead and count our electrons. We know that there's going to be 2 electrons in each covalent bond. So there's 2, 4, 6, 8 electrons. Just like that. So the answer for number 9 is B, 8 electrons. Using the VSEPR model for number 10, what would you predict the shape of the NH3 molecule to be? So ammonia. Let's go ahead and draw it again. Just like that. So we got our NH3 molecule, and we have to remember a few things. First of all, a tetrahedral geometry would look something like the ammonium ion, where there are 1, 2, 3, 4 atoms bonded to the nitrogen and no lone pairs. That's what makes up a tetrahedral geometry. So we can't have a tetrahedral geometry here because we have a lone pair. We have 1 lone pair. So it cannot be tetrahedral. And let's take a look at linear. So if it were to be linear, it would look something like this molecule. And we've seen this before. So CO2 here is an example of a linear molecule. So the angle that's between these bonds is 180 degrees. That would be a linear molecule, meaning it's literally in a line. And we certainly don't see that here. So the option C is incorrect. And then the last one we have is bent. It might be a little bit closer than linear, but still not right, because in order to be bent, you can think of the structure of water, and remember that for something to be bent, like water, it has to have two lone pairs. A lone pair here, and a lone pair there on your central atom. Okay, so it requires there to be two lone pairs, and here we only have one. So it's neither linear nor bent. So just by the process of elimination, we are left with trigonal pyramidal. But I want to go in a little bit more in depth and actually understand why it's that. So let's take a look at this molecule again, and imagine here that I've got the extremities of my fingers here representing the hydrogens, and they're pointing towards the nitrogen. Let me see if I can kind of align it here. Okay, there's where my nitrogen is, and the ends of my fingers here, where I've got my knuckles here, that's going to represent the hydrogens. So if I did not have a lone pair there, yeah, it might look a little bit more like this. But since I've got that lone pair there that's going to push the electrons away, remember VSEPR theory involves repulsion, so the electrons from the hydrogens are going to repel from the lone pair. And so in doing so, that's going to take this and bend it like this, away from that lone pair, so that you maximize the distance that the electrons are apart from each other. Let me grab a different color here and see if I can demonstrate to you why it's called trigonal pyramidal. So if I draw this out like this, and this is like a corner that's coming out at us, out of the page, here's another corner, and I connect this like so, you can see, hopefully from my drawing you can see, that this starts to look a little bit like a pyramid. So it's called trigonal because you've got 1, 2, 3 hydrogens there, and pyramidal because on the bottom here you have a pyramid. So this only happens, just to summarize, this only happens when you have 3 atoms attached, or bonded technically, to the central atom, and if you have one lone pair on the central atom. So you get those two things to be true, and you now have a trigonal pyramidal geometry. Alright, so there we go. That's quiz number 3, or excuse me, quiz number 4. So of course, if you have any sort of questions, please feel free to get in touch with me. Okay, thanks a bunch.